Welcome back. In this video, we will introduce analysis of variance. So let's go ahead and jump right in. So we'll start by defining the analysis of variance model. What does it tell us? How are we representing our data with this model? We'll talk about some assumptions that are needed in order for us to do analysis of variance on a data set. And then finally, we'll talk about how to interpret analysis of variance, what it tells us about our data, and more importantly, what it can't tell us. So let's jump right in. Analysis of variance, or ANOVA, starts with a central null hypothesis. So we are assuming, or we're trying to test, whether or not K groups in our sample have the same population mean. So for example, if we take 3 different treatment groups for a drug that's supposed to lower cholesterol, do they all have the same mean cholesterol at the end of the experiment? What we're looking at with analysis of variance, or ANOVA, is a starting assumption that all members of our population have the same mean. In other words, that grouping K doesn't explain anything about the variability in our data. Any differences that we're seeing, just due to random chance. Think of this like extending the 2-sample t-test to more than 2 groups. We're going to see how we can compare 3, 4, 5, and so on. So our alternative hypothesis in ANOVA looks a little bit like this. Our alternative is that at least one of the K groups, possibly more, are different from the rest. So we write this as HA, mu I is not equal to mu J. So there's at least some group that's different from the rest. In order to work with analysis of variance, we need to understand what the model for this looks like. When we do analysis of variance, we're taking each of our observed values, so our y sub ij, I indicating the group, j indicating the subject within the group, and we're breaking it up into 3 different parts, or 3 different components. The first part is some overall population mean, which we'll call mu. We're assuming that all of our observations underneath have the same baseline, the same mean. Then we're adding or subtracting some additional effect, and we call those group effects alpha. Some groups will be a little bit above that overall population mean. Some groups will be a little bit below that overall population mean. We capture that group variability with the alpha term. Then the last term, epsilon, represents the little bit that's left over. Just due to random chance, some subjects will have a slightly higher value, some will have a slightly lower value. We capture that variability that is not due to the grouping in that epsilon term. So let's take a look at an example to really illustrate how this process works. So we have a data set here of 12 observations split into 3 groups. So group A has 4 members, group B has 4 members, and group C has 4 members. Each of the members in these groups has integer values, so y right here. If we take a look at a plot of this data, so here each bar represents an individual observation. The shading represents the different groups. We've got group A in kind of a pinkish coral, group B in green, group C in blue. It looks like overall group A tends to have the lowest values of y, group C tends to have the highest values of y. How can we explain this? Is there really something to these groups being different? Do the groups explain the variation? Or is this just due to random chance? So how are we going to look at this? Well, we'll start by coming up with an overall group mean. So ignoring the groupings, some overall mean for all 12 observations. Here I've chosen to use the favestats function to calculate that. I get a mean of 2.25. I've added that to my plot here with a red line. So we can see that some observations tend to be higher than the mean, some tend to be lower. The observations above the mean are coming from group C or maybe group B. The ones below the mean, group A and group B. So there might be something to this. The next step is to try to tease out those group effects, those alpha terms, and here's what I'll do. I'll calculate the average now within each group. So we'll call those the group means. The group mean for group A is 7.5. The group mean for group B is 12. The group mean for group C is 17.25. Take a look at how those compare to the population mean, though, now graphed in black. Group A has a negative effect. Group A tends to be below the mean. Group C has a positive effect. Being in Group B bumps you up a little bit compared to the overall population mean. Group B is actually right at the population mean. There's not much added or subtracted from being in that group. Now, the last thing that we want to do is see, well, how far does each individual observation go compared to its own group mean? What are the individual deviations? And these are the epsilons, now indicated in red. Some of these epsilons or these differences from the group mean will be large, some will be small, some will be negative, some will be positive. Here's our question. Are we explaining more of the variation in the data with these individual deviations or with the group deviations? So we'll fit this model in R using a function called AOV, standing for analysis of variance. We'll write that we'd like to do an analysis of variance, so that's the AOV function. Our response variable y changes depending on group. So you can read that tilde as depends on or is a function of that group variable. Our data set here is just simply called data. We'll take a look at a summary of this model and get a table back called the analysis of variance table. We'll go more in depth as to what each of the parts of this table mean very shortly, but look for something we recognize. This is a probability. This is a p-value. So this is measuring the strength of evidence for or against that null hypothesis. In this example, we have a low p-value, which indicates strong evidence against our null. So at least one of these groups is different from the rest. We can reject the null hypothesis that all groups have the same population mean. So that's the basic outline of how an ANOVA test will work. There are some assumptions that we make when we use this method, or there are some conditions that must be met for analysis of variance to be appropriate. Here's the first basic assumption of our model. Whatever that mu, that population mean is, whatever the group effects alpha are, whatever the population variability, which we're representing with a sigma here, whatever these are, they're constant. In other words, we're assuming that they are not changing within the population. Second assumption that we're making is that the ANOVA model is additive. In other words, we're just adding values together. We're not, say, multiplying by some group effect. Third assumption is that the error terms are independent and identically distributed. So there's no link, in other words, between the subjects in our data. They're all independent, they're all distinct from one another, so their errors should be as well. We also are assuming that these error terms follow a normal model with mean 0. So in other words, some will be positive, some will be negative. They'll average out to 0. Here's our last assumption. Our last assumption is that the population variances for each group are equal. So that means that group A has about the same level of variability as group B, which has about the same level of variability as group C. Kind of like that equal variances assumption from the previous video. So let's take a look at a real data example. We have a study that was done in dentistry to evaluate the effect of tooth etching time on resin bonding strength. So we have a total of 78 undamaged, recently extracted first molars or baby teeth that were randomly assigned to be etched with phosphoric acid gel for either 15, 30, or 60 seconds. So we're doing this study on real human teeth. We're choosing to use baby teeth because they have been removed in a clinical setting and will be later replaced. So there's no ethical implications here. Composite resin cylinders of identical size are then bonded to the tooth enamel. The researchers examined this bond strength after 24 hours by finding what's called the failure load. In other words, how much force do they have to apply in order for the bond to break? So a higher failure load indicates a stronger bond. So let's start by writing the ANOVA null and alternative hypotheses. Our null hypothesis is that all groups have the same population mean, in this case the same population mean failure load. So the mean for the 15 seconds group is the same as the mean for the 30 seconds group is the same as the mean for the 60 second group. Our alternative hypothesis is that at least one group has a different mean. It might be that 15 is different from 30, might be that 15 is different from 60, might be that 30 is different from 60. We don't know yet. Our alternative is just that there's at least one difference. So taking a look at the data, does it look like there are significant differences in the failure load? Absolutely. If we take a look at the 15-second etching time, these tend to fail somewhere between 0 and about 7 megapascals. 30 seconds has a bit higher in terms of the typical failure load. 60 seconds is even higher in terms of the typical failure load. There may be some differences in variability here as well. If we take a look at the size of the box in these box plots, in other words, the range of the middle 50% of the data, the 15-second group looks to be the least variable. The 60-second group looks to be the most variable. So we may have some problems with that equal variance assumption. Let's start by estimating the group effects, the alphas, and the grand mean mu. Now, in order to get that grand mean mu, or the overall population mean, we'll take the mean of our data without respect to the grouping. So our overall average failure load is about 6.41. Our group effect then is the difference between the individual group means and the overall mean. So for the 15-second group, we'll take the mean of that, so 4.24, subtract the population mean 6.408, we get a negative effect, negative 2.16. So the 15-second group has a lower than average etching time. The 30-second group has a group effect of negative 0.026. The 60-second group has a group effect of positive 2.192. Now, if you add these group effects together, you should get 0. The group effects will average out. Now let's take a look at the test statistic in this. So the test statistic for analysis of variance is what's called an F statistic. This F statistic is actually a ratio. The details for calculating this can be found in your textbook. We won't go into those in this video, but here's the basic idea. We come up with two measures of variability, what we're referring to as mean squares, so average squared deviations. The mean squares attributable to the group, or the MS for group, is a measure of the variability between the different levels of each factor. So the variability with group A compared to the variability of group B compared to the variability of group C, for example. Then the mean squared for error measures the leftover variability, what's not explained by the grouping. Now, let's do a little thought experiment. If the mean is the same for all of the groups, then we wouldn't expect to see much variation from group A compared to group B compared to group C. So that mean squared for groups should be small. There would be a lot more variation associated with the random error. So if we have a small F statistic, the mean squared for group is much smaller than the mean squared for error, well, that suggests that the grouping doesn't explain much. It doesn't tell us much about the variation in the data. However, a large F statistic is going to suggest the opposite. That's going to suggest that we're explaining a lot more variation with that grouping term than we are with the error term. Now, software programs will typically report these results in an analysis of variance table or an ANOVA table, like you saw in a previous slide. The basic outline of this table is always the same. There's a lot of calculation that goes into this, and again, there's formulas in your textbook for doing this by hand, what I want to do is just highlight the most important parts of this ANOVA table, the things that I like to look at. The first thing I like to look at is this degrees of freedom column, or this DF column. For me, I use this as a sanity check. So I like to use this to make sure that the model that I fit is the model that I intended to fit. So for my groups, or my treatment, the degrees of freedom are the number of groups K minus 1. So in our dental example, those degrees of freedom should be 3 groups minus 1, so should be 2 there. The total degrees of freedom are the number of observations n minus 1. Then the error degrees of freedom are n minus k. If there's a mismatch between what I expect to get and what I get in my software output, that tells me something about my data. Specifically, that tells me that my data might not be formatted in the way that I'm intending. The next thing I look for is the p-value. I don't worry so much about those mean square group and mean square error when I'm interpreting the test. I like to base my interpretation based on that p-value. Again, we're not looking for a binary interpretation here. Yes, we reject. No, we don't reject. This p-value is giving us a strength of evidence. In some cases, we might be convinced by a higher p-value than in others. It just depends on how much evidence we really have gathered and the quality of that evidence. So let's take a look at this model. So in order to fit the ANOVA model, I'm again using the AOV function. In my data set, the failure load variable represents the failure load. The etching time tells us how long the teeth were etching. So here I've written that failure load depends on, or is a function of, etching time. The data set is called tooth etch. When I'm running multiple models, I like to make sure that they have different names. So here I've just simply named my model results.teeth. If I take a look at a summary of this results.teeth model, here I get my degrees of freedom are 2, 3 groups minus 1, so that's a good sign. That means that we have read in and formatted the data correctly, essentially. Our p-value here is 0.0003, so it's very small. Based on this sample, based on this p-value, we have some pretty strong evidence to reject the null hypothesis. What that means is that we can conclude that at least one of these treatments has a different failure load than the rest. Now, here's what analysis of variance on its own doesn't tell us. We know that at least one group is different from the rest. What we don't know yet is which one. We will look at some methods in class this week that we can use to tell us a little bit more about which one is different. That's it for this video. I'll see you in the next one. Bye.